Imagine you own a watch that lets you travel through time. One day you get the bright idea to travel back to the 1920s to mess with your grandparents. Since you've never been the highest fan of your grandfather, you decide to push him out over the edge. Gravity does its thing, and a few seconds later, no more Pappy. But wait, if you killed your grandfather before he ever met your grandmother, you wouldn't have been born to be able to go back in time and kill him. Here's the problem. If you didn't exist to kill your grandfather, you couldn't have killed him. Because you didn't kill him, he's still alive. But that would mean that you yourself would be alive, and now you can go back in time to kill him. And so the endless loop goes on. This is called the grandfather paradox, and it's part of what makes time travel so interesting. Let's say you and I are wearing identical watches and we synchronize them right before I blast off into space. In the space shuttle, I'm traveling roughly at 28,000 kilometers per hour relative to the Earth. If I make a few orbits around the Earth before I return home, when we compare watches, we'll see that less time has passed for me. A very, very tiny amount of time, but is there nonetheless. This is called time dilation, and it simply means that according to Einstein's theory of relativity, time measured along different trajectories is affected by differences in either gravity or velocity, each of which affects time in different ways. One example of time dilation is when we compare the passage of time on the ISS versus on Earth. After spending 6 months on the space station, astronauts have aged approximately 0.005 seconds less than those of us here on Earth. Interestingly, the effects of time dilation are fairly minor, even up to around 70% of the speed of light. However, once we reach 75% or so, the effects become dramatic. Possibly the strangest aspect of special relativity is that distances shrink in the direction of motion. When we think of traveling to a point 10 light years away at 90% of speed of light speed, you'd expect it to take 11 years, right? That's not exactly the case. To a stationary observer, it would indeed seem to take your vessel 11 years. But to the people inside the vessel, not only time but distance would dilate, and you would reach that point in only 4.4 years. If you were to return home from your 90% light speed trip, you would be 9 years older. But everyone back on Earth would have aged 22 years. So in essence, you have traveled 13 years into the future relative to your time in space. And there you have it, people. That was time travel. That was time travel explained by Randall Garcia.